Hello everyone, and welcome to the show. It's me, your ichino-ani. Today is August 18th, a wonderful Monday, and you know what that means. It's time to pull a super interesting, trending article from the archives. Today's paper is from the field of machine learning or arXiv. The title is, a little bit of a mouthful. Are you ready? It's efficiently verifiable proofs of data attribution. arXiv.org/forward/abs/2508.10866. Wow, that's a long one, isn't it? So let's break this down together. What problem is this paper trying to solve? Well, it's all about trust, everyone. Imagine a giant super smart AI model. It's been trained on mountains and mountains of data. Now, when this AI makes a decision, like saying a picture is a cat, we might wonder why. Which of those millions of trained pictures were most important for this one decision? Answering that question is called data attribution. It's super useful. But there's a big problem. Figuring this out is incredibly expensive. The paper mentions that for one project, they had to train 3 million, yes, 3 million different models just to figure it out. This means only huge companies or labs with tons of computers can do this kind of analysis. Let's call them the prover, like someone who is proving something. But what about the rest of us? What about smaller companies or researchers? Or even just regular people who want to use these results? Let's call them the verifier, the one who needs to verify. How can the verifier trust that the big, powerful prover did the calculations correctly? What if the prover cheated a little to save money, or to make their own data look more important? It's like the prover did some really complicated homework, and the verifier wants to check it without having to read all the math themselves. The paper points out that a simple check doesn't work. You can't just check if the prover's answer has a low error. Why? Because a sneaky prover could give you an answer that has a low error, but isn't the best possible answer. It's good, but not great. And that difference could mean someone gets paid less, or a biased decision isn't properly fixed. So this paper comes up with a super clever solution. It's an interactive protocol. Think of it like a conversation between the little verifier and the big prover. The verifier, who doesn't have a lot of computer power, asks the prover to do a bunch of calculations on many different, random pieces of the data. Then, and this is the really smart part, the verifier does a spot. The verifier secretly picks just a few of those calculations and does them all by themselves. It's just like when I checked your homework, right? I don't have time to check every single problem for every student. But if I picked 3 random problems and you got them right, I can be pretty sure you did the rest of the homework honestly too. If the prover's answers on the spot match the verifier's own work, the verifier can trust all the other results the prover sent over. And using those results, the verifier can now easily check if the prover's main answer, the data attribution, is nearly the best it can possibly be. The most amazing part is that the amount of work the verifier has to do, the number of spot nicks, doesn't get bigger even if the dataset is huge. It only depends on how accurate the verifier wants the check to be. This makes it super efficient. So, what can we use this for in our daily lives? Let me give you 3 examples. First, let's talk about fair data compensation. Imagine a future where you get paid for the data you provide to train AI. Maybe it's your photos or your reviews of products. How much you get paid would depend on how important your data was. A big company, the prover, would calculate this, but how do you, if they know they're paying you fairly? With this method, you could check their work and make sure they're not trying to pay you 50% less just to save some money. But it ensures fairness for everyone contributing data. Second, think about trustworthy medical diagnoses. The doctor uses an AI to look at a patient's x-ray. The AI says, I think there might be a problem here. The doctor, being very careful, will want to know why the AI thinks so. The hospital's giant computer system, the prover, can show which past x-rays from other patients influence this diagnosis. The doctor, as the verifier, can use this protocol to quickly check if that explanation is reliable. This helps the doctor make better, more confident decisions for their patient's health without needing a supercomputer in their office. And for our third example, let's think about making AI fair. Sometimes, AI models used for things like hiring can be accidentally biased. To fix this bias, engineers need to find out which data in the training set is causing the problem. A company, the prover, might say, We found the biased data, and we're fixing it. At an outside auditor we verifier, I'll want to check this claim. This protocol let them verify the company's findings efficiently, making sure that AI systems are becoming fairer for everybody. Now, how does this compare to other technologies? Well, the paper explains that just checking the error, which is a simple approach, is not enough. Malicious prover can easily fool that kind of check. This new method is much stronger because it checks if the answer is close to the best possible answer. You might also think about super secure cryptography methods. Those can prove that a calculation was done correctly. But you can't prove that the calculation was done on the right data, or that the result is actually useful. The prover could do a perfect calculation on bad data, and the cryptography check would pass, but the result would be meaningless. This paper's method, called verification, is different because it checks the statistical quality of the final result itself, which is what we really care about. So to wrap it all up, this paper gives us a wonderful tool. It's a way for people with less computing power to trust the results from powerful AI systems. It's like a verify system for the age of AI, making sure everything is fair and correct. What a fascinating idea, right? That's all the time we have for today. Join me again next time for another exciting paper. Bye-bye, everyone.